Hello everyone and welcome back. Since CIE examinations for October-November 2023 are just around the corner, I figured it's a good time that we took a pause on some handwritten lectures and instead revisited some of our past papers. Now last time we were going through paper 1, variant number 2 for May-June 2023. So today as a continuation, we're going to dive into paper 2 of AS level physics for the series of May-June 2023. And do note that this is the second variant we're looking at. Okay, so let's start things off with the first question. So here it says, we first have to define pressure. Now, since this is a 1-mark question, it helps to just keep our sentence as brief as it can be. So in this case, it's just a matter of remembering the formula for pressure, which is force per unit area. So it's just a matter of writing this out. So it's the force applied per unit area, right? If you wanted to, you could have also written it like this as well. It's merely just taking the written word, it's basically taking the statement and just writing it in terms of formula. Both work, as long as your statement is brief. Now comes the second part. Use the answer to AI to show that the SI base units of pressure are kg per meter per second square. So here we have to remind ourselves that when we're talking about SI base units, it's basically us breaking down some kind of formula or some kind of SI unit for a derived quantity and writing it in terms of the base units of kg for mass, meters for length, or second for time. So we can always start things off by first writing out the formula for pressure. Pressure equals force per unit area. And then we just have to break down each formula as much as we can until we can write something that can be written down in its simplest base units. So here we can first take a pause and write the formula for force using Newton's second law, where force represents mass times acceleration. Mass times acceleration over cross-sectional area. This kind of substitution works because now all of our units, or all of our quantities rather, can be written in terms of base units because that's precisely what their SI units are. For mass, we know the SI unit is kg, so I can write that directly. For acceleration, I know the SI unit is meters per second square, divided by the SI unit for area, which should be meter square. To simplify things now, it's just a matter of resolving the meter indices. So I can write kg and per second square as it is. But for meters, I have to resolve it and simplify the indices. 1 minus 2. And in the end, I should get kg per meter per second square. So that's my first answer that we have proven correctly. Alright, let's go to the next question now. Now we have the following. A horizontal pipe has length L and a circular cross-section of radius R. A liquid of density ρ flows through the pipe. The mass m of liquid flowing through the pipe in time t is given by the following formula, where P1 and P2 are the pressures at the ends of the pipe and K is a constant. So now we just have to determine the SI base units of K. Whenever you have to find the SI base units of an unknown quantity, it helps to make K, our unknown, the subject of the formula first. So let's do that. We write down the formula as it is, m equals pi P2 minus P1 r raised to the power 4 rho t over 8kL. I can keep everything as it is. I can just replace m with k. So in more detail, that would mean multiplying both sides by k and then dividing both sides by m. So in the end, I should get k equals pi P2 minus P1 r raised to the power 4 rho t divided by 8mL. So now I have to basically take this formula and now simplify the SI units wherever I can. It does help to write out each term's units separately before plugging them into our equation. So for that, first things first, we can definitely ignore things like pi and the constant 8. Because they're simply constants and constants are unitless. So we can basically ignore these unitless quantities. So Apart from that, let's look at the other quantities. Now when you have P2 minus P1, this is nothing but the difference in pressure. So I could write this as delta P. And a difference in pressure still has the same SI units as pressure, right? And so I can replace it with the formula that I'm already familiar with. In fact, we solved it in the previous question. That is kg per meter per second square. Next for R4, R is the radius and so is a unit of length. So in terms of its SI units, it would be meter raised to the power 4. Rho is density, which is mass per unit volume. In terms of a formula, that would be kg per meter cube. And then finally, for T, that's time, so that would just be second. And then L is the length L, and so that's directly meters. Now that I have all of my SI units precisely as I need them, now it's just a matter of me one more thing. So M is also the mass, so let's write that out as kg. Now I have everything I need and now I just have to plug the SI units into the formula that's given. And I can do that over here. So I have kg per meter per second square times meter raised to the power 4 kg per meter cube and times second divided by kg times the length L. Notice how once again I ignored the units for pi and 8 because they're unitless and so basically you don't have to include their units. Now I just have to simplify things. So kg cancels out with this kg and then I can write the SI units I already have, meters to one side, per meter, meter is to the power 4, minus 3, second minus 2, second over meter. This meter can cancel out with this meter to give me m raised to the power 3. And then m raised to the power 3 completely cancels out with m raised to the power negative 3. These cancel out. And I'm left with per meter per second square. Oh, there's also kg as well. So I'll write that too. And then per second square times second times kg. And then I get kg per meter. And then minus 2 resolves with plus 1 for the s over here. And we get minus 1. So these are the SI units for K. Specifically the SI base units, right? Now let's move on to the next one. An experiment is performed to determine the value of K by measuring the values of the other quantities in the equation in B. The equation is already given over here. Now, state and explain quantitatively, the values of L and R each have a percentage uncertainty of 2%. State and explain quantitatively which of these two quantities contributes more to the percentage uncertainty in the calculated value of K. Now for K, the formula that we are given, and in fact we rewrote was this, so I'll write it as it is, pi times P2 minus P1 R raised to the power 4 density time, and then we get 8 ml, right? And the percentage uncertainty that we are looking at is for L and R. So I can ignore the rest for the moment and only focus on L. We can focus on L and R. So if I want to express the percentage uncertainty within K, let me write that here. The percentage uncertainty for K in terms of the percentage uncertainties of the length L and R radius, it would just be an addition of their percentage uncertainties. However, for the radius R, I have to keep in mind that there's a power given to the radius R, and that power will appear as basically a factor or a coefficient in front of the percentage uncertainty of the radius. So even if L and R both have the same percentage uncertainty of 2, in fact if we plug that in, notice how there's that coefficient of 4 basically increases the contribution coming from the percentage uncertainty of the radius R. So even if they have the same percentage uncertainty, out of the two quantities, it's going to be the radius r that contributes the most. So you'll basically first state that and then explain why that's happening. So to state it, you'll write that the radius r contributes most to the percentage uncertainty of k. That's your stating part. And then to explain it, you'll say it's because of the coefficient 4 with the percentage uncertainty of r. Right? So there is this, you could also rephrase this as saying that there is going to be 4 times the effect, or 4 times greater would be the effect of the percentage uncertainty of L. You could either say it in terms of a comparison or just explicitly mention the coefficient itself, right? And it's in relation with the formula. So that does it for this question. The first question for this paper, where we basically saw how we can break down a formula into its SI base units and then with a formula that's already given, determine the SI base units of unknowns and then see how through that formula you can compare percentage uncertainties. Alright, in the next video, we will dive into the next question of the same paper. Thank you.